Welcome back. Okay, welcome back. 2 weeks from tonight will be November 5th, and that'll be our midterm exam. It'll be closed books, no notes, no calculator. I'll probably be more lenient at the final and give you at least a page of notes. But I figure, heck, we haven't even done anything. It's just the midterm, so you'll easy to memorize, easy to remember. One of the things that I do think it's important is that you remember Maxwell's equations in differential form. Okay, so that is key. Now, the material to be tested on we'll cover through tonight's lecture. Okay, so that's why I kind of like to freeze the material 2 weeks before the test. So if there's any questions, you have time to chase me down or very, very good TA and talk about it. Yeah, so that's the reasoning for that. And tonight we will more or less get through or finish up the last little bit of transmission lines. Okay? On Monday we'll have a lecture that at least will be fun for me. Hopefully for you too. And then we'll get into antennas. Okay? We will have probably a few weeks at the end of the semester. And I indulge myself with various and assorted electromagnetics topics that I like to teach, and are all important. If you have a preference, somebody was mentioning that they wanted to see rectangular waveguides, for example. I'll take those under advisement as well. Although I will note that there is a bit of gratuitousness in there. If I haven't lectured on something in a little while and I feel like doing it, I'll do it. You know, it's the end of the course. You know, we'll have covered most of the required material, so I can be a little bit indulgent, I suppose. So again, I've noticed that since I think putting the lectures online is sort of a mistake when it comes to attendance. And I hope the people who are not coming to class at least do watch the videos. And for their benefit, they should notice that there's a midterm Wednesday, November 5th, closed books, no notes, no calculator, with the material through tonight, which is this class. Okay? All right. Let's go forward. Now, we've been talking about transmission lines, and I'll just hit some of the highlights that we've done here. Configuration where it's really not a circuit problem, but we discretize it with small little bytes so that it is a circuit problem. Lumped impedances. We derive the telegrapher's equations for that. We solve these telegrapher's equations by turning it into a wave equation. Second derivative in space, second derivative in time. I solved this in a slightly different way. I'll be more conventional tonight, I promise. But the way I solved it last time was through a coordinate transformation. I moved into a moving reference frame that moved along with the voltage. And I was able to show that as long as my reference frame was moving at the same speed of light as the disturbance, I could find a solution to it. The other way to interpret that is that any shape any shape voltage will work so long as it travels at the right speed of the transmission line. And the transmission line will make it travel at the right speed. That's not really a problem. Okay? And what's nice about that is we're not restricted to sines and cosines. Remember, this is a telegrapher's equation, and we want to be able to send random data, seemingly random bit streams along this transmission line. Okay? So any old shape will work: sawtooth, triangular, random ones and zeros, dots and dashes. The reason that this is not different from what we did before is the magic of Fourier series. We solved transmission, we solved Maxwell's equations, we solved these kinds of problems for one harmonic. And so now we can add up all the harmonics together and get whatever shape we want. And the reason we can do that is by the strict nature of these constants. As soon as we have some variation in those constants, perhaps a frequency variation or what have you, different frequency components will move at different speeds, and all of a sudden I can't have a general moving reference frame for all components of my signal. Okay? That's where the real world steps in. Okay? We substituted back in, and we found the current, and what that allowed us to do was come up with the concept of an impedance, and that's a very, very important concept for what we're going to talk about tonight. Is the fact that this transmission line has a lumped impedance, and we're familiar with that from the vernacular of working in the labs. 50 ohm, 75 ohm type of transmission lines. We can then look at boundary conditions, which is the termination of a transmission line. And again, we're going to pick this up in more detail tonight. And so we see that what we really have is, in terms of this boundary condition, in terms of terminating line, everything has to do with the transfer from one lumped impedance into another lumped impedance. That's the bottom line here. So if we have a mismatch of impedance with the line and the load, we have a reflection. If RL is not equal to Z naught, we have a reflection coefficient. This, by the way, is exactly an analogy to what we had with plane waves against a dielectric or a lossy dielectric. So, and similarly, we will transfer some of our power into some of the voltage into the load, and that transmission coefficient is given here. We solved it fairly straightforward by some algebra and the appropriate definitions. And again, this is an exact analogy to what we did with plane waves against a dielectric. Okay. We looked at some special cases: open line, short-circuited line, and a matched line. And we have various reflection coefficients and transmission coefficients. I'll leave it to you to show that the maximum power transfer, I haven't said anything about capital R and capital T, so the maximum power transfer occurs in this special case. Okay? So what you might do is consider the power in the line versus the power in the load and optimize that. And you'll find that happens when RL is equal to Z naught. And you'll see exactly how much power gets transferred in there. Okay? All right. I did this all for a pure resistive load, but you can automatically generalize it to have both a reactance and an admittance part, a real part and an imaginary part, which will include some mesh structures, or even another transmission line. Okay. We'll talk a little bit about that, I think, on Monday in some bizarre contortion of a case. Okay. I treat it just a little bit differently. All right, so let's go back to the natural solutions to the wave equation, which are the sines and cosines. Okay, so these are our natural solutions, and we can borrow back from what we had before with the general case of the voltages and the currents. And so we can write voltage as a function of Z and T is equal to a voltage moving in the positive direction plus a voltage that's moving back in a reflected manner or a negative direction, in a duplex manner. And that's really what we solved for before, except now I'm going to put in sines and cosines for this. And the current scales by the impedance of the line. Think about that as cleaning up units. Maybe a little bit more serious than that, but not so much. And here not only do we have the movement of the disturbances, the direction of the disturbances inside the parentheses, but the current direction changes sign, and so I have a minus sign there as well. So now I'm going to consider the special case of sines and cosines, and I'm going to say v positive as a function of z and t is equal to v positive, an amplitude, and I'll launch a cosine. So I'll launch with definite phase. And it's always traditional when you do that to, I think, pick a cosine. Okay? And this is actually kind of we work so much with complex notation that we sometimes forget how nice it is to keep definitive track of phases. And the way we can do that is we have a reference cosine, and then we look responsive with cosines that are out of phase. If we want to write that as sinusoids, sines, that's fine too. So v plus is equal to a cosine. Here's my disturbance. Here's my traveling coordinate system, and I'm scaling it to a particular frequency, omega. Okay. If you go out and you say omega over v, that's k. Right? That's 2 pi over the wavelength. That's k. So this is almost identical to what we had before, if you consider the dispersion relationship. And I encourage you to get comfortable with that. Okay? So that's what this term here is, of the outgoing V positive pulse. And for an arbitrary load, I'm going to have some reflection. So I know a little bit about what to do. V minus of z and t. So I know I'm going to have some magnitude that's coming back at me. I can eventually write that as a reflection coefficient, but for now I just know it as some amount of volts that are coming back at me. I know that I'll have a sinusoid, and I know my direction of that sinusoid will change, but I don't know the phase that's going to come back at me. I don't know the length of the transmission line. I don't know how much capacitance or inductance further delays the spitting back of that. Yeah?
V on the denominator?
You're right. Sorry. I'm surprised you can tell the difference with my handwriting between a V and a Z. Thank you. That's really... Okay. Yeah, that should be a V. Now it's just a splodge, but we all know that it's a V. Where was I? Oh, we have to include a phase shift. We have to include a phase shift. And so I will add an arbitrary phase shift term that, we'll have to figure out what that means. Okay? All right. So now I'm going to think about my reflection coefficients. And we remember that my reflection coefficient was RL minus Z naught over RL plus Z naught. And what I'll do is I'll go ahead and I'll generalize these, as I've told you we can do, that I'll have a complex load, a complex impedance for RL and Z and Z and so I'll have rho is equal to ZL minus Z naught over ZL plus Z naught. Okay. And now that I've introduced all kinds of complex numbers in there, remember my transmission line could be complex if it's lossy, right? So now that I've introduced that, I'll argue to you that reflection coefficient is made up of a real part and an imaginary part. And I've written this in Cartesian form, but I could just as easily write this in polar form. So this total delay here, this is, if you think about a time delay in its Fourier transform, this is a delay term here, and this is the delay of the total delay of the transmission line, and then whatever extra cycles the complex load has. So right as well, I have a transmission coefficient, a voltage transmission coefficient. And again, that's complex in general. And so again, I can write that in polar form or Cartesian form. So I know the relative amount of these guys can now be given in terms of rho. And notice what I've done. I've gone ahead and written omega v as beta or k. Okay? Most people who work in RF and microwave like to use beta. Most people who work in optics like to use k. It is, I will admit, as an optics person, that beta is a lot more fun to write than k. Now, for the sinusoidal waves inside of a transmission line, we often use what we've seen before, which is the standing wave ratio. And this is going to be V max over V min. And the maximum is going to happen at a very magic, let's say t equals 0. It's kind of arbitrary. So we lose these guys here. But it's going to happen at a magic z such that this guy and this guy add up in phase. Okay, so there'll be a z where these guys add up in phase, and that will be the maximum voltage that we're going to get. So that'll occur and this will happen at a particular L. And I can solve for that L. So I can substitute that back in. So we'll be at a position L, and at an arbitrary time equals 0. And that's going to equal That's just straight substituting in. And so that'll equal V plus cosine theta rho over 2. And then my reflection coefficient looks something like that. It's in the L. It's in the L. The beta goes away with the L. So this guy goes away because it's 0. I've got a beta and I've got a Z. L is equal to theta rho over twice beta. So that beta cancels with that beta. Do you see that? Is that a yes or a no? I'm sorry, what?
You're trying to get the Z and now you're substituting it for Z so the beta cancels out?
Yep, exactly right. So yes, it's a good question. The maximum occurs at a particular Z whereby this relationship holds. This adds up in phase with this guy here. And I'm saying t equals 0. And so minus this guy here, minus beta times Z at a magic L, will equal positive beta Z plus theta rho evaluated at that particular L. So now I substitute in, minus beta L is equal to beta L plus rho, plus theta rho. And so I'll have twice beta L plus theta rho equals 0. And then I solve for L. When I solve for L, I shove it back into this equation here and here. And the beta cancels. Okay? Sorry, I should have said that. I should have gone into that in more detail. The important thing is I've got this cosine term here, and I've got this 1 plus rho sitting out over here. Well, the V minimum occurs when the cosines subtract. So that's minus beta Z evaluated at L is equal to beta Z evaluated at L plus the phase shift of the reflection plus pi over 4. Okay, that means that it'll be sufficiently out of phase to flip that around so that so there's a minus sign there. So we can solve that for L. Let me make this L prime so we know that it's not the same L that we had before. I'll skip just a couple of steps. Give you something to do tonight when you can't sleep. And so I have an L prime. And if I shove that back in there, I'll get a V minimum. With the same cosine term. But now I explicitly say that this term is the minus of that term. And really you could have figured that out right from the get-go. You could have intuited that. But this just gives you just a slightly more rigorous approach to thinking that through. Okay? But you know that this number is going to be bigger when this term and this term add together, and it's going to be smaller when this term subtracts from that term. So, not really huge. So now if I take the standing wave ratio, is Vmax over Vmin. Vmax over Vmin, you can see I'm going to cancel the V pluses, I'm going to cancel the cosine terms, and I'm just going to be left with these guys here, which we've seen before, in fact. So the standing wave ratio, V max over V min, is equal to V plus cosine theta rho over 2 times 1 plus the absolute value, or the magnitude of the reflection coefficient, V plus cosine of theta rho over 2 times 1 minus that magnitude. So cancel, 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 cancel. 1 plus rho over 1 minus rho. And that's S. Or I can rearrange that as rho is equal to S minus 1 over S plus 1. And we've seen exactly those relationships before. Okay, it's just a little bit of a review. Perhaps because there's a test coming up on November 5th. And as a good professor, I like to review. You might also think in terms of getting, there's a couple of lines of algebra getting from there to there, but not too much more. All right. Let's go back to this expression. And let's remind ourselves that that's equal to, in Cartesian coordinates, the complex reflection coefficient. And what I'd like to do here is I'd like to divide through by the transmission line. Okay? So I'm just normalizing to 50 ohms or 75 ohms or whatever my transmission line environment is. And the nice thing about that is I now have an expression that's unitless. And so I'll write that as a script Z. And I'll solve for that script Z. And that's equal to 1 plus rho over 1 minus rho. Yeah?
Is rho primes equal to I rho double prime or in addition to?
Oh, I'm so sorry. It's equal to a plus. Ugh. In the signals and systems class, one of the folks brought in a whole bunch of cookies, and you would think that I would have actually partaken in one of those cookies with that kind of a mistake, but I was wise enough not to. So I still make the mistake. Never eat baked goods of arbitrary origin on a college campus. This one's probably a lot safer than most. All right. Oh, yes. Now, this Z load is made up of a reactance part and an admittance part, a real part and an imaginary part, right? So I'm going to write that as R plus IX. So those of you who are enjoying writing that script L, it's gone now. Sad. I know. So if I look at this guy here, I write R plus IX is equal to 1 plus rho prime plus I rho double prime. That's just separating out the rho into its real and imaginary part in the numerator. And this is 1 minus rho prime. Right, because that's where the minus sign comes from. Minus I rho double prime in the denominator. And now we notice that there's an I in the denominator. So we do what we always do, which is clear that out. By multiplying by 1. Let me know if I flip the pages too fast. Just yell at me and I'll go back. And so R plus IX is equal to 1 minus rho prime squared minus rho double prime squared plus I twice rho double prime divided by 1 minus rho prime quantity squared plus rho double prime quantity squared. So now I have a real part here, and I've got a real part here, and I've got an imaginary part here, and I've got an imaginary part here. So because I indicates an independence or an orthogonality, I can set the real parts equal, and I can set the imaginary parts equal. So I have R is equal to 1 minus rho prime squared minus rho double prime squared over 1 minus rho prime squared plus rho double prime squared. And I have X is equal to twice rho double prime over 1 minus rho prime squared plus rho double prime squared. Now, it's customary to organize your equations on a real and imaginary axis, right? And so in this case, the imaginary is rho double prime and the real is rho prime. So I can imagine an axis, rho double prime and rho prime. And I have to think a little bit about what rho means. It's my reflection coefficient. Now, it's nice to think that I could have an amplifier there and get rho's bigger coming back at you than going outbound. The truth is, most transmission line problems are passive, and so I probably won't have that. Well, not in a classroom setting. But certainly in a lab or certainly in industry you might run across that. But anyway, if that's the case, then there's a maximum rho that can ever be. The magnitude of rho, voltage reflection coefficient, is going to be 1. You neither lose anything nor gain anything. And so the magnitude equal to 1 means the rho prime squared plus rho double prime squared, square rooted, will equal to 1. And we call that a circle. With a radius 1 for the maximum value. So the magnitude of rho must be less than or equal to 1 without gain. Without any amplifier in the system. Okay? So if it's lossy, if there's losses in the system, the radius will be smaller. But if there's no loss at all in the system, like what we've been looking at, then we're going to be on this unit circle. Okay? So just keep that in mind. Okay? Any questions so far? All I've done is algebra, right? Same concepts, just introduced complex notation and done it. So I have two equations. And at this point, we can rearrange these equations. And some of you will recognize the form of this rearrangement. It's a circle. 0 and a center there, and and radiuses that look like that. So this is a circle. Radius 1 over 1 plus r. And it's centered. And I'm still thinking this rho prime and rho double prime plane. Okay? So the rho double prime plane centered here is along this axis here. And the center rho prime will walk up here depending on how much r and 1 plus r is. Okay? I'm sorry. I think I said that wrong. Rho double prime equals 0 is the center is always going to be here at the rho equals 0 case. So how far it is along our rho prime is going to depend on the r over 1 plus r. Okay? So if I go back to my axis, rho double prime, rho prime, for r equals 0, my radius will be 1. My center will be at rho double prime equal to 0 and at rho prime equal to 0. So the circle that I drew here is, in fact, this equation. R equal to 0. 1, 1, 1, and 1. Okay? For r equal to 1, my radius is a half. And it's still along the rho double prime equals 0 axis. And for rho equals to 1, I have a 1 over 1 plus 1, or a half, makes my center here. And my circle, let's see if I can get this right, fits snugly into there. So this is the r equal to 1 circle. You could infer that if I'm between 0 and 1, my center is going to scooch over and I'm going to have a circle that's kind of in between these guys. Okay. For r equal to 2, my radius is 1/3, and my center is at 2/3. So I scooch over here. Notice that I'm 1/3 of the way from there. So I'm always going through this point here. But I have a circle that looks something like that there. And that's my r equals to 2. So all these circles go through this point here, are tangent to that point, or to each other, and go through that point there. And then it's just a question of how much I move into that. So how much loss shrinks down my signal? Okay? So rearrange the x equation. And again, after some algebra, I can come up with an equation for a circle. The radius is 1 over x, and it's centered at rho prime equal to 1, and at rho double prime equal to 1 over x, the same as the radius. So now if I come back to my rho double prime and rho prime axis, there's my unit circle, really poorly drawn. This point is 1. So my center of my circles will live on that line there. See, the rho prime equals to 1. So at rho prime equal to 1, I'm going to have my circles either up or down on this. The center of my circle is either up or down on that. So for the x equal to 1, the radius is 1 over 1, or 1. The rho prime is going to be on here, and the rho double prime is going to be at 1. So that means my center is up to here. And I'm drawing an arc that looks like that. And if it continues outside the boundaries, it goes up something like that. It's fun and easy to do -1. The radius is going to be 1. And the center is now going to be down here. And I'll have a circle that looks like this. And this is my x equal to 1, and this is my x equal to -1 circles. Okay? At x equal to 1/2, my radius is 2. And I'm centered up at 2. So my center is going to be somewhere up there. And my circle is going to be something like that. Or for the -1/2 case, it'll be something like that. Okay. And for x equal to 2, the radius is 1/2, and it's centered at 1/2 So I'll have curves that look like that. And so you can fill in as you need to there. Okay. What did I just derive? Have you seen that Smith? Have you seen this derivation before? But you've all used the Smith chart, right? I know. I'm always surprised about that. Okay. And now at least you've seen where the Smith chart comes from. Okay. And that's kind of nice to know. And you see that it's not magic, right? It's just a small amount of it. It's just algebra that gets you into this form.
This is half of 2, x equal to the right.
Oh, you're right. I blew that, didn't I? These are the 2's. These are the 2's. I got messed up with my 1/overs. Sorry about that. Okay. And I'll see if I have a clean copy of the Smith chart to show you. I may not. Yeah. Here's a good one. Here's one as good as any. Okay. And so this is what I do that right? Yeah. So anyway, so this is a more or less clean copy of a Smith chart. And in the old days you could buy these by paper. Nowadays you could probably still find them online and print them out so that you can do old paper calculations on that. I even have somewhere in my office, one of a former student was kind enough to give me what's it called? Not a slide rule, but a plastic nomograph of a Smith chart where I was able to slide one around the other and do my calculations on a Smith chart. I think I figured out how to work it once, and it would take me another 15 minutes to refresh my memory on it. Okay? In case you didn't notice, I'm not the hugest fan of using the Smith chart. I am being a little sarcastic about it, and partly, and I don't mean to. I know you spent a lot of time working on it. I know it helps you a lot. But the one point I want to make about it is the Smith chart is horribly single frequency. All the calculations that you do are for a particular resonant frequency, which is fine if you have one frequency, but you know how boring it is to listen to a single note of a song, right? Whenever you send data down a line, whenever you're trying to do even a complicated radar chirp signal, you're going to have a complexity you're going to have a plurality of frequency spaces, of frequency components. And the trend that I see is a larger and larger spread of spectrum. Okay? A larger and larger spread of spectrum. And so for that reason, there are other techniques that can be used and probably should be used to get frequency dependencies and complex structures of transmission lines with linked elements on them and all. And I want to go over an approach next time that begins to accept that and trades out the slide rule nomograph paper mentality to algorithms that lend themselves really nicely to MATLAB. Okay? So I'm not going to just slam it. I'm also going to suggest a direction to go that gets a little bit more modernized. Now there's a price to that. You have to learn it and you have to kind of get comfortable with it. And probably a while you should match up the two. But that's just sort of another perspective. Okay, I'm glad. How many of you guys feel fairly proficient with the Smith chart? Yeah, I'm not. Yeah, after you go through the great Randy Lehman courses and Rashonda courses, you should be, right? So I don't have to waste your time on that. Let's see. I have just a couple more things to do for you. Excellent. Okay. All right. Now, do you remember when we looked at the examples of the coax line, I also showed you the lost parts of it, right? I showed you there was resistive losses and there were lossy dielectric losses. And what that's going to do is it's going to fundamentally change the telegrapher's equations. Okay? And so in addition to a lumped inductance and a lumped capacitance, I'm going to have additional elements that talk about the resistive loss as the current flows through this wire, and I'm going to talk about the dielectric loss as the electrons on the chains of the dielectric molecule travel up and down the chains, but pay a tax to do so, or pay a toll to do so, and lose energy in that as they bounce off each other, as they brush up against each other. There will be an absorption loss in the capacitance. Okay, and so if you do that, your new lumped element model looks like that. So I have an I at Z and T flowing in. Flowing out, I have an I of Z plus DZ at T. I have a voltage on the input. I have a voltage across the output. And now these output currents and voltages are influenced not just by the inductance, per length, but also a resistance of the wire and a conductance of the dielectric. And now if I do my Kirchhoff's voltage law, in addition to the L dIdt term, I'm also going to have an R times an I term. So my new telegrapher's equation for my voltage we didn't have this term before. That's what we had before. And now we have a loss term that goes linearly with current. That's my V equals IR, Ohm's law. And if I do Kirchhoff's current law, and there are some steps there that I think you'd enjoy doing to refresh, to review and learn, but that's the answer. If I do Kirchhoff's current law, I get a new loss term due to the lossy conductance of my dielectric. So these two loss terms are now new. So, let's go ahead and solve these equations. And I'm going to, let's see, how do I want to say this? I'm going to assume a cosine dependence for time. I'm going to assume a form of separation of variables so that I have a function v of z, which can be anything, and a cosine omega of t. If I substitute this into the equation, what I'll end up doing is Fourier transforming it. Okay? At least the voltage terms. So this separation of variables with a particular harmonic in time is the equivalent of Fourier transforming the differential equations. Okay? Things don't work out quite as well with the current. Okay? Because of the losses, the relative amount of reactance and admittance, the relative amount of the real part and the imaginary part of this circuit element is upset. And so I don't know how much cosine term I have versus how much sine term I have. So this is the current that is in phase with the voltage, and this is the current that is quadrature or out of phase to the voltage. Do you guys like the term quadrature? Do you know it? I know some of you know it. It's a favorite of mine. So in phase and quadrature, because out of phase would just be too obvious and too easy to communicate. So we have to invent a new word. Oh well. Okay. And by the way, I've the I prime and I double prime are that's fairly obvious relationship between the in phase part and the out of phase part, real part, imaginary part. So if we substitute this into this equation here, I'll have the cosine term and the first derivative of the envelope there. And then I'll have sines and cosines terms for that one there. Okay? So I will have minus del V naught del Z, and that's at cosine omega t. And that's going to equal R I prime of Z cosine of omega t plus R I double prime of Z sine of omega t. That's my substituting into my V equals IR term. I get the in-phase part and the out-of-phase part that goes through the resistance. And then I do clean up the time derivative. Now remember, cosines and sines are orthogonal. So I can find a time when the sines go to 0. And then I have these three terms that have to equal each other. I can find a time when the cosine terms go to 0, and then I have these two terms have to equal each other. So I can set the cosine coefficients in one equation, the sine coefficients the other equation, because sines and cosines are 90 degrees out of phase. So for the cosine terms, I'll call this equation A. And then equation, the sine terms show that the real part and the imaginary part are just scaled relative to each other. So I can combine these guys together. And what I've done is I've solved the equation in time. And I have a ordinary differential equation for V in Z in terms of one component of my current. If I take these and I substitute into this equation here, I get that. So I'll just have a sine and a cosine term there, and then I'll just have the sine term coming into there and the cosine term there. So if I solve for the cosines and I solve for the sines, And I'll call this equation B and equation C. If I go back to this equation A, and I take the I take a derivative with respect to z, I will have del 2v del z squared here, and I'll have a del I prime del z term there. There's my del I prime del z term there in terms of v naught. Okay? If I take the d by dz of this term here, I have a d I naught double prime dz, and there's my di out, my di 0 double prime dz in terms of v naught. Right? So take del by del z of equation A and sub in B and C. And that eliminates the current from that one equation. Clean this up a little bit. And I get that. And the correct, it may not be quite obvious from the mathematics of a second order differential equation, but if you think in terms of what the loss is trying to tell you, and knowing that the square root of -1 will help you out if it needs to, the right guess is actually an exponential. And you'll see that that works. There's nothing wrong with that. You'll pull down a gamma squared here and still have an e to the minus gamma z, and you'll pull down, and you just have an e to the minus gamma z. So we'll solve the equation. And you're comforted by the physical expectation of that. And so your gamma, if you substitute that in and solve for gamma, you'll see that it's the square root of Rg times 1 minus omega squared LC over Rg to the 1/2. And you can go back if you want and either solve those equations for I or you can differentiate here to get I prime, and then do your scaling to get I double prime. Okay, so that represents a full expression. How much time do I really have? 4 minutes? Okay. With that, we can say that we can generalize this problem, this transmission line problem, to any lumped impedance. So I'll have a Z impedance per length little z, and I'll have a y dz there. I, v, v plus delta v, I plus delta I. Okay, so we've Fourier transformed this in time so that we can use our complex impedances. And my new transformed telegrapher's equations. Whoops. Look like that. If I differentiate this and I substitute this in, I get that term. And I'll have exactly the same differential equation, the e to the minus gamma z that I had before, where that's my gamma. This line will have a new characteristic impedance. Z naught is equal to this over this. That's my generalization for L over C. And that'll allow me to scale between the voltage and the current.